Hello and welcome to Easy Introduction to Statistics. I'm Hobin Kwok and I'll be your instructor for this course. Today, we're going to delve into the fundamental concepts of statistics. If you're interested in machine learning, data analysis, or data science, understanding statistics is crucial as it provides the core principles and methodologies essential for these areas. Even if you haven't studied statistics formally, having a grasp of basic statistics is increasingly vital in the data-driven world. Therefore, I'm confident that this lecture will serve as a solid base for your further exploration into machine learning and data science. To fully understand statistics, it's crucial to focus on the core concept that it is a discipline centered around dealing with data, specifically extracting insights and deriving conclusions from data. Statistics is a very comprehensive field of study, covering almost every aspect of data. The field of statistics is broad, encompassing various categories such as data sampling, data description, data analysis, and lastly, data inference, which entails making predictions or decisions based on data analysis. Additional subcategories within statistics include experiment design, an aspect that focuses on planning experiments in a manner that enables the statistical measurement of their effectiveness and facilitates the comparison of results. It involves planning and structuring experiments to effectively test hypotheses while controlling for variables that could affect the results. Data description, on the other hand, entails graphically or numerically portraying data to compare their characteristics, such as their distribution. Data inference is a statistical method used to make predictions based on available data. Additionally, there are several other subcategories in statistics, including data sampling and the Bayesian approach, which offers a distinct perspective on data. These are just a few examples of the subcategories that make up the field of statistics. Throughout this lecture, rather than attempting to cover every aspect of statistics, our main focus will be on these two crucial subcategories: data description and inference. We won't delve into other areas such as experiment design, the Bayesian approach, or categorical data analysis for this course. By the end of this course, you'll possess a strong foundational understanding of these two categories at a basic level. Before we dive directly into statistics, let's first familiarize ourselves with some key terms used in the field. In statistics, terminology is crucial because it strictly distinguishes between the concepts of populations and samples. Indeed, in statistics, populations and samples are clearly differentiated. Suppose we identify a characteristic of a population and label it A. There will also be a corresponding A in samples. Although they are conceptually similar, the meanings or interpretations of A are significantly different. Theoretically, statistics is the study of populations, using samples as a means to understand a population. The reason behind studying samples in statistics is to eventually generalize insights to the population. Therefore, the process of studying data typically begins with samples. Consequently, when making inferences about a population, we rely on information gathered from its samples. However, using population terminologies when discussing samples can lead to significant confusion. In summary, in statistics, it's essential to be careful when selecting terms, as there are distinct terminologies for populations and samples. A population represents the entire group that a researcher wants to draw conclusions about, or generalize findings to. The concept of a population is foundational in statistical analysis as it forms the basis for making inferences and drawing conclusions. The definition of a population is the entire set of individuals, items, or events that are of interest to a researcher. Next, a parameter is a numerical characteristic that describes a population. Parameters are key values that summarize important features of the entire population being studied. They provide essential information about the distribution, variability, and other properties of the population. For instance, the average online gaming time of high school students serves as a parameter, where high school students represents the population and the average daily online gaming time represents a numerical summary of the population's behavior. Again, parameters are the numerical summary of a population. Similarly, the percentage of adults who prefer cats over dogs exemplifies parameters within statistical analysis. In this context, the entire adult population constitutes the group of interest, with the percentage of preference per cats serving as a numerical summary. A sample is a term in statistics that corresponds to a population. But it's important to note that a sample is a subset of a population. However, a sample not only represents a portion of a population, but also accurately reflects its characteristics. A sample is not just a random subset of a population, and it must appropriately capture the population's characteristics. In essence, a sample is a representative subset of a population that captures its essential characteristics and variability. Additionally, just as a sample corresponds to a population, a statistic also corresponds to a parameter. Thus, a statistic is a numerical summary of a sample. Here are examples of statistics similar to what I have seen earlier. In both examples, we have specific numbers like 1,000. If the entire number of high school students is 300,000 or 1 million, we only selected 1,000 students among them. Thus, a group of 1,000 high school students is a sample from the population. Consequently, statistics include a process of examining statistics of a sample and inferring parameters of a population based on the statistics of the sample. Thus, the fundamental flow of an inference begins with these two concepts below and eventually leads to the two concepts above. It's crucial to note that our primary focus lies in understanding what parameters are. When we calculate the mean of our sample data and so on, it's all geared towards inferring the parameters of the assumed population and explaining the population itself. As we explore statistics, we'll come across different types of data. These data sets represent our samples, and by employing techniques like visualization and other statistical methods, we'll extract insights about the population. We can categorize data types into two main categories: categorical data and quantitative data. Categorical data are often referred to as qualitative data, while quantitative data are commonly known as numerical data. Categorical data represents characteristics or attributes such as blood types like A, B, and O, occupations like teacher, doctor, and engineer, eye colors like blue, brown, and green, or grades like A, B, C, and so on. However, although both blood types and grades are considered categorical data, they possess different characteristics. While each value of both data types can be divided into categories, grades exhibit a hierarchical relationship, with an A being considered higher than a B and a B higher than a C. Conversely, the relationships between blood types are not hierarchical. For instance, it's difficult to determine if blood type A is higher than blood type B or O in any meaningful sense. To distinguish between these data types, we further categorize categorical data into two subtypes: nominal data and ordinal data. Nominal data is a type of categorical data that represents categories or groups without any inherent order, ranking, or numerical significance. On the other hand, ordinal data is a type of categorical data that represents categories with a natural order or ranking. In other words, ordinal data are data such as satisfaction level that have a relative size that can be compared with other values. Unlike nominal data, ordinal data provide information about the relative magnitude or order of the categories. On the other hand, quantitative data can be represented numerically. However, just as we have both integers and real numbers in number systems, discrete data consists of whole numbers or integers and represents distinct and separate values. Discrete data can only take on specific distinct values without any intermediate values between them. Continuous data, on the other hand, is a type of quantitative data that can take on any value within a given range and can be measured infinitely precisely. The most significant feature of discrete data is that it is countable, such as frequencies and the number of defective items. In contrast, continuous data is uncountable. For instance, you cannot count every real number between 0 and 1. If you can count them all, please leave the number in the comments. They are uncountable because there are infinitely many real numbers between 0 and 1. Length and time serve as examples of continuous data. If you don't understand why they are not countable, let's think about it this way. Length, such as height, is not countable since there are countless numbers, for example between 170 and 171 centimeters, such as 170.1, 170.11, and so on, depending on how accurately you're measuring heights. There are infinitely many possibilities within the range, and that's why length and heights are continuous data. Distinguishing between data types is crucial because the approach to data analysis varies significantly depending on the type of data. Most of the data we'll handle in this course, such as when practicing statistical inference, linear regression, hypothesis test, and so on, will be quantitative data. However, delving into the analysis of categorical data, which we won't cover in this course, requires exploring a separate subfield with its own unique approach and methodologies. Ensuring accurate categorization of data isn't just the first step. It's a crucial one in applying the appropriate statistical analysis technique. Therefore, the ability to distinguish between different types of data is essential. Furthermore, even though specific types of data may not be explicitly mentioned, as you progress through the lecture, you should develop the skill to differentiate between discrete data, characterized by distinct and separate values, and continuous data, which spans a continuum of values based on the context and characteristics of data being discussed. Being able to classify data into appropriate types will make data analysis easier. Let's explore some descriptive statistics such as mean, median, and mode, which may already be familiar to many of you. These three statistics are measures of central tendency in statistics that help describe the center of a data set. Let's start with the mode. The mode is simply the statistics that represents the most common value in a data set. Consider the table displayed here. Suppose in the first column, we have shoe sizes ranging from small to extra large. And in the second column, we have the corresponding number of pairs of shoes sold. So out of a total of 40 pairs of shoes sold, which size is the most common? It's the medium size with 25 pairs sold. Therefore, the mode of this data set is the medium size. In summary, the mode is the value that appears most frequently in the data sets. A key characteristic of the mode is that it is largely unaffected by extreme values. For example, imagine the number of shoes sold for the small size increases to 15, but the numbers for the other sizes remain unchanged. The overall distribution of the data set barely shifts. Now, let's say the sales for the small size increased further to 20, and the sales for the large size bumped up to 21. the differences between the numbers are relatively small. Then imagine the sales for the extra large size drop to 0. Since the number of sales for the extra large size is relatively small compared to other shoe sizes, it's an extreme value. Although we have an extreme value in our data set, the medium size remains the mode, illustrating the most robustness to extreme values. As demonstrated in this example, the mode is primarily used for categorical data. Imagine we gathered height data from a sample of 1,000 individuals, recording measurements to 2 decimal places, and constructed a data table using Excel. However, in this table, it becomes challenging to pinpoint values with significant frequencies, like the medium size with 25 sales from the previous example. If we extend our measurements to 3 or even 4 decimal places, we'll likely observe lower frequencies for each value. Consequently, the mode becomes more applicable for categorical data sets with a small number of distinct categories. Additionally, it's worth noting that a data set might exhibit multiple modes. If the number of sales for large shoes jump to 25, both medium and large sizes will represent modes within the data set. The median represents the central value of a data set when its data are arranged in order, regardless of whether they are sorted in ascending or descending order. For instance, if we consider a data set consisting of natural numbers from 1 to 9, the median would be 5, the value at the center. In this example, our data is already sorted. However, if the data set is not sorted, we need to sort it first before determining the median. Now, let's consider another data set comprising natural numbers from 1 to 10 with an even number of data points. There's no single value at the center of the data set. In such instances, the median is calculated as the average of the two central values. Similar to the mode, the median is less sensitive to changes in observed values or the presence of extreme values. Consider a new data point 99 next to 9. Obviously, it's an extreme value. However, despite this extreme value, the median of our updated data set remains at 5.5, still in close proximity to the original median of 5. Calculating the median involves identifying the relative position of the central value within a sorted data set. Moreover, even when values change from 1 to 1.1, 2 to 2.1, 3 to 3.1, etc., the median is less sensitive unless its relative position changes and it remains close to its original value, 5. It's one of the key characteristics of the median. The median is a descriptive statistic used frequently in both categorical and quantitative data. I also use the median quite often at work as a data scientist. For instance, when faced with extreme values within a data set and seeking a statistic that best represents its central tendency, I use the median. The median serves as an excellent measure of central tendency, particularly adept at handling data sets with extreme values. Now, let's delve into another statistic, the arithmetic mean, often referred to simply as the average or just mean. The arithmetic mean is the most commonly used type of mean in real life. It entails summing up all the values in the data set and dividing the sum by the total count of numbers. This statistic measuring central tendency is widely utilized due to its simplicity and intuitive understanding. However, because it involves summing up all values, the arithmetic mean can be influenced by both the presence of extreme values and changes in the data set's values. For example, suppose we have natural numbers from 1 to 8, with one large value 999. In this scenario, it is evident that 5 represents the central tendency of the data set, as it is the number located at the center. However, when we calculate the central tendency using the arithmetic mean, the extreme value of 999 significantly influences the summation in the mean calculation, resulting in a mean value around 100. Consequently, the arithmetic mean of the dataset is too large to accurately represent its central tendency. This is one of the limitations of the arithmetic mean. To mitigate this issue, we can use a trimmed mean, which calculates the mean without including extreme values. Once again, the arithmetic mean can be calculated by summing up all the values in a dataset and dividing the sum by the total count of numbers. Now let's delve into the weighted mean. The arithmetic mean serves as a generalized form of the weighted mean. The calculation method for the weighted mean incorporates weight into the equation, as depicted below. By adjusting certain parameters within this formula, we can derive the equation used for calculating the arithmetic mean. Essentially, the equation for the arithmetic mean is a broader interpretation of the equation for the weighted mean. In contrast to the arithmetic mean, the weighted mean explicitly incorporates weights into its calculation. Within a dataset, some data might be more important than others and vice versa. For example, grades for a full-year course might be considered more important than grades for a half-year course. You know, we are happier when we get an A+ for a full-year course than we get an A for a half-year course. Similarly, you might be happier if you get an A+ for a mandatory course than if you get an A+ for other courses you need to take for breadth requirements. The calculation method for the weighted mean is also very simple. The only difference between the two equations is that the equation below includes W's. The W's within the equation represents weights, signifying the relative importance of each data point. The scale of these weights is entirely subjective. You can adjust them to reflect the importance assigned to each data point. Whether you scale the weights so that their sum equals 0 or assign arbitrary values, the key requirement is to divide the sum of the products of the data and weights by the sum of the weights. Now let's consider how we derive the equation using the formula below. When all weights from W1 to Wn are set to 1, we obtain the numerator of the equation. If all weights are set to 1, given n weights, the sum of weights becomes n, indicating each data point contributes equally to the calculation of the weighted mean. Thus, it becomes evident that the arithmetic mean is indeed a generalized version of the weighted mean. So far, we've explored 4 distinct types of statistics used to measure the central tendency of a dataset. Now, we turn our attention to the final measure of central tendency, the geometric mean. Unlike the arithmetic mean and weighted mean, which involve addition and division, the equation for the geometric mean entails multiplication and root extraction. While the geometric mean might not be as commonly used in the arithmetic mean in real life, it holds significant relevance in certain fields. Personally, working in the financial sector, I find myself using the geometric mean almost daily. However, its frequency of use may vary among data scientists in different domains. The geometric mean is particularly valuable for calculating the average rate of change or growth over time. For instance, it's commonly employed to determine the average profit rate of a specific stock over a period, such as 5 days with returns of 1%, 3%, 5%, and even 10%. You might initially consider using the arithmetic mean for calculating average investment returns, but the geometric mean is preferred when dealing with rates of change over time. Once again, the geometric mean is useful for datasets with values that multiply together, such as growth rates, ratios, or rates of return. To calculate the geometric mean, we begin by multiplying all the values in our datasets, then take the nth root of the product, where n is the number of data points we have. However, can the value inside the root be less than 0? Technically, yes, but generally no. So let's consider a case where the product of our data is less than 0. For instance, suppose my investment profit rate is negative for 3 days, say -1, -3, and -5. Let's substitute -1, -3, and -5 into x1, x2, and x3. Then the product of these numbers results in -15, which is less than 0. Consequently, the negative number goes inside the root, making the calculation more complex. To handle this, when some of our data points are less than 0, we add 1 to each value, like 1 plus x1, 1 plus x2, and so forth. Suppose we have 5 data points within a data set. We calculate the product of 1 plus x1 to 1 plus x5, and then take the fifth root of this product. After obtaining the fifth root, we subtract 1 to derive the proper geometric mean. It's worth noting that we subtract 1 outside the root rather than subtracting 1s inside the root. So when calculating the average return of a stock, each daily return value is incremented by 1. If a daily return is 1%, it becomes 1.01. Similarly, if a daily return is 10%, it becomes 1.1. Let's practice with examples. In Class 1, there are 30 students, and in Class 2, there are 50 students. The average score for Class 1 is 70, while for Class 2, it's 80. Again, the average score for students in Class 1 is 70, and for Class 2, it's 80. How do we determine the average score for both classes combined? Let's examine how the average score of 70 for Class 1 was computed. The left-hand side of the equation is 70. The right-hand side of the equation involves dividing some value by 30, representing the number of students in Class 1. Let's denote Class 1 as x and Class 2 as y. The numerator of the fraction is the sum of x1 to x30, each representing the score for an individual student. On the other hand, the average score for Class 2 80 is determined by summing up the scores of y1 to y50 and dividing by 50, representing the size of Class 2. That's how we obtain the average values of 70 and 80. Now, how do we calculate the average score for both classes combined? Let's denote the average score for the combined class as mu. The total number of students in both Class 1 and Class 2 is 30 plus 50, which equals 80. The numerator is the sum of the scores of every individual student in both Class 1 and Class 2. Hence, the sum of these two values is the numerator for the right-hand side of the equation. Got it? So how do we calculate the sum of these two values? The sum of x1 to x30 equals 70 times 30, and the sum of y1 to y50 equals 80 times 50. Thus, the numerator equals 70 times 30 plus 80 times 50, and we can calculate the value for mu. For now, we're gonna skip the actual calculation. Now let's move on to problem 2. To solve this problem, we'll need to understand how to calculate the weighted mean, similar to the example with Grace mentioned earlier. Let's say we received an A+ for Korean class, a B for English class, and unfortunately a C+ for computer class, and a B for science class. Each class corresponds to 3 credits, 2 credits, 4 credits, and lastly 2 credits respectively. Given that the GPA ranges from 4.5 to 2.5 for an A+ to C+, what is the average GPA for all subjects? Since the credits vary for each class, calculating the weighted mean is the appropriate approach. Remember, for the weighted mean, we divide the sum of the products of weights and data by the sum of weights. What are the weights in this problem? In this problem, the weights are the credits representing the importance of each class. Thus, the denominator is the sum of 3 for Korean class, 2 for English class, 4 for computer class, and lastly 2 for science class. The numerator is calculated as 3 times 4.5 for an A+, plus 2 times 3 for a B, plus 4 times 2.5 for a C+, plus 2 times 3 for a B. We can then calculate the weighted mean using the numerator and the denominator. We'll skip the actual calculation once again. Now let's move on to the next problem, which involves calculating the geometric mean. Consider the inflation rates over 5 years, 3%, 5%, 6%, 2%, and 4% respectively. Oh, they're the weird looking inflation rates, and it's not good for the economy. Anyway, how do we calculate the average inflation rates when they fluctuate up and down? Since we have 5 data points, we're going to take the fifth root of the product, which includes 1 plus 0.03, 1 plus 0.05, 1 plus 0.06, 1 plus 0.02, and lastly, 1.04. Don't forget to subtract 1 after taking the fifth root. If you calculate this, you'll get the geometric mean of the interest rates. The final problem involves finding the median of a dataset. Earlier, I mentioned that finding the median is the same as identifying the central data point. However, before we search for the central data point, we must first sort the datasets. Let's arrange the data in ascending order: 2, 3, 4, 5, 6, 8, and 9. Therefore, 5 is the median. Now suppose the dataset does not include the number 5. In this case, our sorted dataset would be 2, 3, 4, 6, 8, and 9. Here we have two values located at the center. In such instances, we calculate the average of the two numbers, which is also 5. Next, we are going to explore the statistics of dispersion. The variance and standard deviation are the statistics that measure the dispersion of a dataset. Dispersion in statistics refers to the spread or variability of data points in a dataset. I will explain why dispersion is significant in statistics. Consider two schools A and B. Suppose a student from school A receives a score of 70 on the final exam, and another student from school B also receives a score of 70. So, are they equally proficient in the subject? In school B, grades are spread across a range from 0 to 100, exhibiting a relative flat distribution. On the other hand, at school A, most grades cluster around 70, such as 68, 67, 65, and so forth. Now, the distribution of grades in school A is very pointy compared to the distribution in school B. In this scenario, can the grades from each school be compared equally? No. Achieving a score of 70 in a highly competitive environment differs from the obtaining the same score in a less competitive setting. In other words, earning an A in a fiercely competitive environment and earning an A in a less competitive one carry different implications. This highlights the importance of the dispersion of a dataset. Dispersion indicates how tightly data points are distributed around the mean, or, in our example, how competitive the environment is. Measuring dispersion not only provides insight into the variability of data points within a dataset, but also allows for comparisons between different datasets. Therefore, when comparing the means of two different datasets, we must also consider their dispersions. Variance is a statistical measure that quantifies the spread or dispersion of a set of data points around their mean value. It measures how far each data point in the dataset is from the mean and provides a measure of the variability or dispersion of the data. The equation here represents the calculation method for sample variance, often denoted as S squared. If we aim to calculate the variance of a population, denoted as sigma squared, instead of dividing the sum by n-1, we divide it by just n. It's important to note that in most cases, parameters of a population are denoted with Greek letters, while statistics of a sample are denoted with alphabets. Once again, when calculating the variance of a sample, we divide the sum by n-1, whereas we divide the sum by just n when calculating the variance of a population. Now let's explore the definition of the standard deviation. The standard deviation is simply the outcome of taking the square root of the variance. The biggest characteristic of the standard deviation is that it is expressed in the same units as the original data. For example, suppose we have a data set of heights from 100 individuals, and we calculated the variance of the data set. Inside the equation for the variance, it has a power of 2, which means that the measure of the variance is squared centimeter, although heights were originally measured in centimeter. Since the measures of the variance and the original data are different, it might not be intuitive to understand how data points are distributed around the mean with the variance. The reason why we use the standard deviation is that in the equation for the standard deviation, it has a square root which returns the variance squared unit to the unit of the original data. I want to emphasize again that the standard deviation is expressed in the same units as the original data. If the standard deviation I want to calculate is the standard deviation of a sample, we denote it with S. However, if we want to calculate the standard deviation of a population, we first take the square root of the sum divided by n. We also denote the standard deviation of a population with the Greek letter sigma. Mastering the computation of variance and standard deviation is crucial in statistics. Thus, it's important to memorize the equations rather than swiftly moving on once you grasp the concepts. I suggest reinforcing your understanding by repeatedly writing the equations and solving problems. As previously demonstrated on the previous slide, the variance equation is presented as follows. Moreover, we can manipulate the equation to take on this form. This particular equation is often employed in proofs to simplify equations. Now let's explore how we can derive the second equation from the first. Let's begin with the first equation. When we expand xi minus x bar squared, we get xi squared minus 2xi times x bar plus x bar squared. Then we divide the sum by n minus 1. Now let's consider how we can reshape the equation to resemble this form. Inside the brackets, certain elements remain unaffected by the summation. We can assert that the elements with a subscript I are those affected by the summation. Hence, the first two terms in the numerator are influenced by the summation, while x bar remains constant. In a sense, as we iterate through the summation from I to n, the value of x bar remains unchanged, repeatedly adding the same value. Thus, we can rewrite the equation as sigma xi squared minus 2x bar sigma xi plus nx bar, since x bars are not affected by the sigma. The denominator is still n minus 1. Now it's time to introduce a very powerful technique that you must remember. Once you understand this technique, you can apply it to simplify equations in statistics and other proofs. While it's simple, it's also incredibly powerful. It's important to remember what it looks like and how it's applied in this proof. Again, it appears very often in other proofs as well. We denote the mean of a sample as x bar, calculated by dividing the sum of all data by the number of data points. Again, you add up all the values in a data set and then divide the sum by the total number of values. From this equation, we can derive that the sum of xi's equals n times x bar. I'll repeat it again since it's very important. The sum of xi's equals n times x bar. Hence, now we can substitute the sum of xi's in the numerator with n times x bar. Let's simplify the numerator. we can rewrite negative 2 times x bar times the sum of xi's as negative 2 times n times x bar squared. Additionally, there's another n times x bar squared in the numerator. By combining negative 2 times x bar squared and n times x bar squared, we're left with negative n times x bar squared. We have successfully derived the second equation. This proof is straightforward, and the second equation we derive frequently appears in other proofs. However, it's more crucial to remember that x bar equals the sum divided by n, and from this equation, we can deduce that the sum of xi equals n times x bar. Throughout this course, we'll encounter many equations, and this technique will recur frequently. Let's move on to the next problem. Suppose the sample size is 10, the sum of the data is 20, and the sum of the squares of the data is 75. Then what is the value of the sample variance? Since our objective is to calculate the sample variance, we'll employ the equation x squared equals the sum of xi minus x bar squared divided by n minus 1. From this problem, we're given that n equals 10, the sum of xi equals 20, and the sum of squared xi equals 75. Can you use this information to calculate the sample variance? Although we know the values of sigma xi and sigma xi squared, we cannot directly substitute these values into the equation because the numerator involves the sum of xi minus x bar squared. Hence, we need to manipulate the numerator before substituting these values. Let's expand the numerator. The equation can be expressed as the sum of xi squared minus n times x bar squared over n minus 1, following the process we employed in the previous problem. Now we can substitute the given values. Although we don't have a given value for x bar, we know that x bar equals the sum of xi's divided by n. Thus, x bar equals 2, and consequently, x bar squared equals 4. With these values in hand, we can now calculate the sample variance. Next, let's explore some statistics that describe the shape of a dataset, starting with skewness. Skewness indicates whether data points are evenly distributed or tend to lean more towards one side. In other words, skewness is a way to measure whether the distribution of numbers in your data is balanced around the mean, or if most of the numbers tend to be on one side of the mean. A perfectly symmetric data set has a skewness of 0. A skewness value less than or greater than 0 indicates that the data set is not symmetric. Consider positive skewness. This might be confusing to remember at first. When skewness is positive, the data set has a long tail extending towards the right-hand side. Conversely, negative skewness means the data set has a long tail extending towards the left-hand side. While you can memorize these concepts as positive skewness meaning a right-hand tail and negative skewness a left-hand tail, I encourage you to approach understanding skewness from a different angle. Positive skewness indicates that there are extreme values exceeding the data's central values, resulting in a long tail that extends towards the right-hand side. This long tail suggests that data points continue up to the tail's end. Essentially, while bulk of the data centers around the mean, there are outliers or extreme values that stretch far beyond these central points, giving rise to the right-hand tail. Again, large values contribute to the extension of the tail towards the right-hand side, as they exist on the right side of the distribution. To clarify, when I mention large value, I was referring to the values that are larger than the central or mean value of the dataset. Likewise, negative skewness denotes a long tail extending towards the left-hand side. We observe a left tail in negative skewness for the same reason as a right tail. Relative to central values such as the mean, median, and mode, smaller values reside on the left side of the distribution. As these smaller values continue up to the end of the left tail, a long left tail emerges. Let's recap. Positive skewness indicates the presence of extreme values larger than the central values. This results in a long tail extending towards the right-hand side due to the large extreme values. Conversely, negative skewness suggests extreme values smaller than the central values, leading a tail stretching towards the left-hand side. In the absence of extreme values, the dataset tends to display relatively symmetric characteristics. Depending on whether skewness is positive, negative, or zero, the relative positions or order of mean, median, and mode also change. When skewness is zero and the distribution is symmetric, the mean, median, and mode all have the same value. However, when skewness is positive, it indicates the presence of extreme values larger than the center. Precisely speaking, a dataset can exhibit positive skewness without necessarily having large extreme values. Even a few higher values stretching out to the right can contribute to this skewness. You might want to memorize the orders of the mean, median, and mode in different skewness scenarios like this: positive skewness, mode, median, mean; negative skewness, mean, median, mode, and etc. However, instead of relying solely on memorization, consider approaching it this way. Do you recall which statistic measures central tendency and is easily influenced by extreme values? It's the arithmetic mean. Let's consider a dataset with large extreme values. When calculating the arithmetic mean, it is significantly impacted by these extreme values, causing it to shift towards the right-hand side in comparison to other statistics. This is why with positive skewness, the mean tends to be larger than the mode and median. And comparing the median and mode, the mode proves to be more robust to extreme values than the median. Consequently, the mode stands out as the most resilient statistic, rarely affected by extreme values. Hence, the arithmetic mean emerges as the statistic most vulnerable to extreme values. Positive skewness indicates the presence of extreme values on the right side, leading to a shift of the mean towards the right. Similarly, in the case of negative skewness, the mode remains the statistic least affected by extreme values, while the mean emerges as the statistic most influenced by extreme values. Negative skewness implies the existence of extreme values smaller than the dataset's central tendency, resulting in a significant leftward shift in the mean's location. Now let's move on to kurtosis. Kurtosis is also a statistical measure that describes shape of the distribution, and it tells us how pointy the distribution is or how fat or thin the tails are. In other words, kurtosis indicates the degree to which data is concentrated around the mean versus how much it spreads out towards the tails. We'll explore the normal distribution further in the lecture, but it's essential to remember that the kurtosis for the normal distribution is 3. Using this reference value, we can determine whether a distribution is more pointy or less pointy. In this final part of descriptive statistics, we'll explore what correlation is. Correlation is a statistical measure that describes the relationship between two variables. We say that two variables are correlated when changes in one variable tend to be associated with changes in the other variable. In other words, we say that two random variables x and y have a correlation when the variation of x and y are related to each other. For example, if values of x and y increase or decrease simultaneously, we can say that x and y are correlated. However, in this lecture, we'll solely explore correlation statistics that represents linear relationships. Does this imply that there are correlation statistics that measure nonlinear relationships? Absolutely, and there are several such statistics available. Nevertheless, for the purposes of this lecture, we'll concentrate solely on linear relationships. Then what is a linear relationship? A linear relationship refers to a relationship between two variables where a change in one variable is associated with a proportional change in the other variable. For instance, if we have two correlated variables x and y, their values can increase simultaneously. Conversely, as the values for x increase, the values for y can decrease. Then, what constitutes a nonlinear relationship? Consider this example. The graph depicts a typical nonlinear relationship. Despite the lack of linearity, it's evident that two variables are associated. Initially, y values decrease rapidly as x value increase, and then from a certain point, y values increase rapidly as x values increase. This illustrates a nonlinear relationship between the variables. If we measure the correlation between these variables, we might obtain a value of 0, indicating no correlation. However, this would be a wrong conclusion stemming from the fact that the correlation statistics we are discussing today only measure linear relationships. The equations for covariance and correlation coefficient indeed look very similar to the equations for variance and standard deviation. Firstly, the method for calculating covariance resembles the equation for calculating variance. The key distinction lies in how the terms are treated. While the variance equation squares xi minus x bar for a single variable, in covariance calculation, we multiply yi minus y bar instead. This difference stems from the fact that covariance involves considering two variables simultaneously. Substituting x into y yields an equation for variance. Consequently, the two equations exhibit notable similarities. Precisely speaking, the equation presented here represents the calculation method for the Pearson correlation coefficient. Developed by Carl Pearson in the late 19th century, the Pearson correlation coefficient is one of the several methods to measure correlation, alongside Kendall's tau and Spearman's correlation coefficient. However, for this course, we exclusively focus on the Pearson's correlation coefficient. Despite its appearance, the equation is not as complex as it may seem. By the way, we denote covariance with the first three letters for simplicity. The Pearson correlation coefficient is essentially the covariance divided by the product of the standard deviations of x and y. Simplifying the equation, we arrive at the formula displayed on the board. Once more, this equation is derived from simplifying the covariance divided by the product of the standard deviations. It's simpler than it appears, isn't it? I will briefly explain how we can derive this equation. Remember, the covariance has a denominator of n-1, and similarly, standard deviation also has a denominator of the square root of n-1. When we multiply these two standard deviations together, we get n-1. Consequently, we can cancel out n-1 in both the numerator and denominator, leading us to the formula displayed on the board. It's not as complex as it may seem, and the Pearson correlation coefficient is simply the covariance divided by the product of the standard deviations of the two variables. The Pearson correlation coefficient, often denoted as R, possesses a significant characteristic. Its value always falls within the range of -1 to 1. This feature is both crucial and highly beneficial. When our data points have large values, the covariance also tends to be large. For instance, consider measuring heights in both centimeters and meters. Regardless of the chosen measurement units, they represent the same height. However, the covariance when including heights measured in meters will yield a smaller value due to the nature of the scale. Heights typically range between values like 1 point something or 2 point something. In contrast, the correlation coefficient disregards the scale of the data points entirely and instead returns a value between -1 and 1. Another feature of the Pearson correlation coefficient is that it only measures a linear relationship. Additionally, as mentioned earlier, it is a unitless measure. I also want to mention that the standard deviation has a measurement unit, although it's the same as the original data. However, the Pearson correlation coefficient entirely disregards units. Furthermore, an absolute value closer to 1 indicates a stronger correlation. A common misconception arises when interpreting negative values of R. It's important to clarify that two variables are uncorrelated when R equals 0. Conversely, when R equals -1, it signifies a very strong negative linear relationship between the variables. This negative linear relationship implies that the variables exhibit a pattern represented by a straight line on a scatter plot sloping downward from left to right. In a sense, as one variable increases, the other variable tends to decrease, and vice versa. Keep in mind that the correlation coefficient can have a negative value when the relationship between variables is negative. Let's move on to a practice problem. We are investigating the correlation between reading amount, denoted as X, and academic performance, denoted as Y. So our task is to calculate the correlation between reading amount and academic performance. Suppose we conducted a study involving 5 students. Again, our goal is to calculate the correlation coefficient between the two variables. To begin, let's outline the equation for the correlation coefficient. Rather than attempting to recall the entire equation at once, let's break it down into its components step by step. So R equals covariance of x and y over the product of the standard deviations of x and y. We normally denote the standard deviations of x and y as Sx and Sy. But for clarity, I will temporarily represent the standard deviations of x and y as Sd of x and Sd of y. We won't be working through the entire equation in this lecture, but I highly recommend that you try solving this problem on your own. If you have any questions about the answer, feel free to leave a comment. Now let's discuss the equation for the covariance of x and y. It's given by the sum of xi minus x bar times yi minus y bar over n minus 1. Given that n equals 5, the denominator is 4. Next, let's determine the equation for the standard deviation of x. It's defined as the square root of the sum of xi minus x bar squared over n minus 1. However, we can simply skip calculations involving n minus 1 since we already know that n minus 1 will eventually be cancelled out. Thus, we can solve the problem only with these two terms. From this point in the lecture, we are shifting our focus to probability and random variables. So far, we've primarily discussed statistics or parameters that describe various characteristics of a dataset, such as central tendency, shape, or correlation. We've also discussed how we can calculate them with different equations. I might have briefly mentioned the term random variable once or twice during the lecture, but I haven't explicitly defined it. In this part of the lecture, we'll explore probability and random variables. It's essential to note that statistics is not only the study of data, but also the study of probability. Furthermore, grasping the concepts of random variables is incredibly crucial as you progress in your studies, particularly in fields like machine learning or in professional environments that demand data literacy. Once you get the concept of random variables, your perspective on data will totally change. Without understanding random variables, a data set is merely a collection of values. However, viewing data as outcomes generated by random variables and probabilities opens up an entirely new approach to data. It's important to note that the concepts I will introduce from this point may seem abstract at first. However, if you pay attention to their interpretations during the lecture, you'll have no trouble understanding them. Before diving into probability, let's clarify some key terms. In statistics, the sample space refers to the set of all possible outcomes or events that could occur in a random phenomenon. It represents the entire range of possible results that could be observed or measured. For instance, let's consider the scenario of tossing a coin twice. If we obtained a head in the first trial and a tail in the second trial, we denote this outcome as HT. Alternatively, we could have obtained two heads in both trials, labeled as HH. Combinations such as two tails or a tail followed by a head are also possible. These four outcomes constitute the entirety of possible results when tossing a coin twice. Therefore, the set comprising these four outcomes constitutes a sample space for the act of tossing a coin twice. An event and a sample space are closely related concepts that are fundamental to the study of probability. Put simply, an event is a subset of a sample space. Once again, a sample space is a set of all possible outcomes, and an event is a subset of this sample space. Given that both the sample space and events are defined as sets, set operations such as union, intersection, and complement can be applied to them. Some of the operations I want to highlight are again, union, intersection, and complement. Additionally, we use the term mutually exclusive to describe two sets that cannot occur simultaneously. In other words, two sets are mutually exclusive when they have no elements in common, meaning they do not overlap. These concepts are fundamental. When computing the probability of something, that something is defined as an event. So when you calculate a probability of something, the input something is always an event. As I previously mentioned, an event is a subset, and it's a subset of a sample space. I've also mentioned that the input for calculating a probability is an event. Thus, when calculating probability, the input is a set, and it's a set of certain possible outcomes. On the other hand, a sample space is a set of all possible outcomes in an experiment, such as flipping a coin twice. When the input for calculating probability is a sample space instead of an event, the probability of getting an outcome within the sample space is always 1, as a probability ranges from 0 to 1. To summarize, keep in mind that both a sample space and an event are defined as a set, with an event being a subset of the sample space. Since both a sample space and an event are sets, they can undergo set operations such as union, intersection, and complement. When I was explaining a sample space, we considered the example of flipping a coin twice. The sample space of flipping a coin twice has four outcomes. In this example, let's define an event A as the event of getting heads exactly once. Once more, event A represents a set of outcomes from tossing a coin twice, specifically those with exactly one head. Thus, we only consider outcomes within the sample space containing precisely one H. Within the sample space of four outcomes, the instances with exactly one head are HT and TH. Therefore, in the experiments of tossing a coin twice, event A is defined as a set comprising HT and TH. Of course, we can use alternative symbols or letters to denote head or tail as long as there is clear differentiation between the two outcomes. In the specific experiment of tossing a coin twice, the sample space is a set encompassing all possible outcomes. Event A is a subset of this sample space following a specific condition, which is outcomes with exactly one head. Now let's define probability. Although there are several definitions for probability, we're going to discuss three definitions among them. Let's start with the classical definition of probability. When there are n equally likely possible outcomes, again, n equally likely possible outcomes, and an event A, which is a subset of the sample space, consists of m of these outcomes, then according to the classical definition of probability, the probability of event A is given by the ratio m over n. Put simply, the total number of possible outcomes is n, similar to how the size of the sample space for tossing a coin twice is 4. When event A consists of outcomes with exactly one head, the size of this event is 2. Thus, according to the classical definition of probability, the probability of event A is 0.5 or 50%. Here, A is not a specific value but rather a set. Thus, when calculating probability, we are determining the probability for a set comprising specific values. Now, let's discuss the empirical definition of probability. Some of you might be familiar with the term relative frequency, which has the same meaning as the empirical definition of probability. This definition estimates the probability of an event based on its observed relative frequency. Additionally, rather than measuring the relative frequency in just one trial, it is assessed over a large number of repeated trials or experiments. The empirical definition figures out probabilities by looking at real data from observations or experiments. Let's revisit the example of tossing a coin. According to the classical definition of probability, the probability of getting ahead when tossing a coin once is defined by the ratio of the number of outcomes in the event, which is getting ahead, to the number of outcomes in the sample space, which consists of outcomes h and t. Event A contains one element, which is ahead, while the sample space contains two elements. Therefore, the probability of getting ahead when tossing a coin once is 1 out of 2, which is 0.5 or 50%. Now, let's explore how we can measure the probability of the same event according to the empirical definition. Instead of calculating the ratio between the sizes of different sets, the empirical definition directly measures probability by repeating the same experiment multiple times. As we repeat the experiment an increasingly large number of times, we'll eventually obtain a probability close to 0.5. The third definition is the axiomatic definition. Also known as the mathematical or formal definition, the axiomatic definition of probability is a fundamental concept in statistics that provides a rigorous mathematical framework for understanding probability. The axiomatic approach to probability means that there are fundamental principles governing the behavior of probabilities. Let's explore what these principles are. Suppose we have a sample space S and an event A as a subset of S. Since probability always ranges from 0 to 1, the probability of A is also a value between 0 and 1. Probability cannot be larger than 1 or less than 0. Additionally, as mentioned earlier, the sample space comprises all possible outcomes, so the probability of the sample space is 1. If there are n elements in the sample space, according to the classical definition of probability, the probability can be calculated as n over n, which is 1. Thus, both the classical and axiomatic definitions share this principle. These two are the first two principles of the axiomatic definition. Moreover, if events are mutually exclusive, meaning that they don't overlap or share the same elements, then the probability of the union of the events is equal to the sum of the probabilities of the individual events. For example, if events A and B are mutually exclusive, then the probability of A union B is equal to the sum of the probability of A plus the probability of B. If the previous three axioms are met, then P of A represents the probability of event A. The axiomatic definition is commonly used in statistics. While other practical definitions are also important, the axiomatic definition of probability is particularly important for statistics exams. So far, we have covered three main definitions of probability: the classical, empirical, and axiomatic definitions. Although the empirical definition may seem less formal as it's based on actual experiments rather than calculations, its importance has grown significantly due to the advancements in computational power and data storage. These advancements enable the measurement of probabilities using an empirical approach. Suppose we want to calculate a complex probability, such as the probability of a certain derivative product not being redeemed before an expiration date. While it's possible to calculate this probability using an analytical approach, it may involve a very complex computational model or be impossible with analytic methods alone. In such cases, we first assume a probability distribution, and then use a method called Monte Carlo simulation, which simulates an experiment multiple times, much like tossing a coin 5,000 times. Suppose we simulate the experiment 5,000 times, and out of those 5,000 outcomes, the derivative product is not redeemed before expiration date 100 times. We can then infer that the probability is 100 out of 5,000. This approach is widely used in many domains, so it's important to understand the empirical definition of probability. Now let's explore some properties of probability. The reason we use set operations in probability is that the input for probability calculations is a set. Therefore, we can perform set operations within probability calculations. The probability of the union of two sets can be calculated as the sum of the probabilities of each event minus the probability of their intersection. Calculating the probability of a complement is also simple. It's just 1 minus the probability of A. Moreover, if events A1 to AN are mutually exclusive, the probability of their union is the sum of the probabilities of each individual event. Lastly, if event A is a subset of event B, wait a minute. This sign also implies the relationship between two sets. Again, when calculating a probability, the input for the calculation is a set. We do not calculate a probability of a single value. Thus, when we are calculating a probability of something, that something should be defined as a set. I emphasize this several times because it's very important. So if event A is a subset of B, then the probability of event A is less than or equal to the probability of event B. I think these properties are pretty straightforward, and many of you may already be familiar with these properties from previous studies. Now it's time to finally discuss conditional probability. Conditional probability is one of my favorite topics in statistics, and I frequently use it in my field as a data scientist. It's also a concept that you must understand firmly to progress to other topics in statistics. Although probability isn't the main focus of this course, it's impossible to continue your studies in statistics and study mathematical statistics or probability theory without a solid understanding of conditional probability. So let's dive into conditional probability. Conditional probability is the probability of an event occurring given that another event has already occurred. Although I use the word occur in the definition, instead of imagining an event suddenly happening out of nowhere, we can interpret it differently. For instance, a given condition such as if the customer is male also constitutes as another event that has already occurred. Similarly, conditions like if the customer is female or if the customer's age is 20 all fall under the category of another event that has already occurred. Therefore, even if the given condition doesn't seem like an event that has actually happened, like the previous examples, you should still regard them as another event that has already occurred within the definition. So the phrase, another event has already occurred, is essentially a given condition for an event. So we've defined conditional probability, and let's explore how we can express it in an equation. The probability of event A occurring, given that event B has already occurred, can be expressed as the probability of A, the event we want to calculate the probability of, given B. Moreover, this conditional probability can be calculated as the probability of the intersection of A and B divided by the probability of B, which is the given condition. Conversely, when A is a given condition, then the probability of B given A is equal to the probability of the intersection of B and A divided by the probability of A. Some of you might already recognize that the intersection operation between two sets is commutative, meaning that the result of intersecting A with B is the same as intersecting B with A. You can simply think of the commutative property as A plus B equals B plus A, where A and B are natural numbers. Thus, the numerators for both probabilities are the same, while the denominators are different. However, there's one more thing I want you to remember. You can also express the probability of event A as a conditional probability. Let's see how we can express it as a conditional probability. Let me erase them so that I can write on a wider space. The probability of A can be expressed as the probability of A given S, where S is a sample space. S is a set of all possible outcomes and event A is a subset of S. In a Venn diagram, if A is a set, S is represented as a rectangle containing A. This equation is intuitive and straightforward because S is a sample space that contains A, and A is a subset of S. Although it sounds very straightforward, let's expand the equation for the conditional probability A given S. The conditional probability of A given S equals the probability of the intersection between A and S divided by the probability of S. As mentioned earlier, according to the axiomatic definition of probability, the probability of S always equals 1. Thus, the denominator is 1, and we can ignore it. Then, what is the probability of the intersection between A and S? Since A is a subset of S, the probability of the intersection between A and S is simply the probability of A. Again, the intersection between A and S is equivalent to A given that A is contained in S. Hence, we can derive the probability of A from the conditional probability of A given S. According to the definition of conditional probability, the probability of A given S is the probability of A occurring given that S has occurred. Let's explore the meaning behind it more conceptually. P of A given S represents the probability of A occurring within the context of S. However, when calculating the probability of A given B, the sample space S shrinks to event B, which is also a subset of S. Again, S is a sample space containing every possible outcome. For example, suppose S is a large set with numerous possible outcomes and B is a subset of S much smaller in size. When the probability of A given S changes to the probability of A given B, the given condition shrinks from a large space to a smaller subset. This is a fundamental concept of conditional probability. When we calculate the probability of A given B, we are essentially recalculating the probability of A but within the smaller sample space defined by event B. Thus, the probability of A given S is generally lower than the probability of A given B, since event B is a subset of S and has a smaller size. In summary, The fundamental idea behind the conditional probability of A given B is the probability of A within the context of the smaller space B. In other words, when we calculate the conditional probability of A given B, we are determining the probability of A occurring within this narrowed down sample space B. So, calculating the probability of an event under a specific condition, such as determining the probability of a refund when a customer is younger than 20, is the same as assessing the probability within a sample space significantly narrowed down from the entire group of customers to a smaller subgroup of those younger than 20. By shrinking the size of the sample space, we narrow down our focus to a smaller subset and calculate the probability of an event within the context of the smaller subset. Please keep in mind this conceptual understanding of conditional probability. Conditional probability is a concept applicable across various domains. For instance, consider an AI model tasked with identifying whether an input image depicts a cat or a dog. Suppose we provide the model with an image and it classifies the image as a dog. We can frame this scenario in terms of conditional probability. Let's denote the scenario of the model returning a dog as event A. Then, the probability of the model returning a dog is expressed as P of A. However, this isn't a straightforward probability calculation, and there are specific conditions to consider. These conditions involve the selection of both the image and the AI model for the task from a multitude of options, effectively narrowing down the sample spaces. Therefore, what we are actually calculating is the probability of the model returning a dog, given that both the image and the model are specific. In other words, conditional probability underpins every application of machine learning or AI models. Therefore, having a solid understanding of conditional probability is crucial. Let's move on to a practice problem. Customers of an insurance company are categorized as either type A or type B. The probability of an accident for a type A customer is 30%. While the probability of an accident for a type B customer is 10%. Suppose 20 of all customers are type A. This means the remaining 80% are type B. Now, what is the probability that a new customer will experience an accident? Let's outline the given information. P of A, which is the probability of a customer being type A, is 0.2. And the probability of a customer being type B is 0.8, as the sample space comprises only these two types. While the probability of a type A customer experiencing an accident is 30%, it should be expressed as a conditional probability rather than simply writing something like P of C equals 0.3. We should use these two pieces of information to express it as a conditional probability. As mentioned earlier, conditional probability is a probability defined within a narrowed down sample space. In this problem, the sample space has been narrowed down to type A customers, and within this narrowed down sample space, customers experience an accident. Thus, considering conditional probability is the right approach to this problem. Let's denote the event of experiencing an accident as event C. So, we need to calculate the probability of event C. However, we have a given condition that the customer is type A. Thus, P of C given A is 0.3. Conversely, the probability of experiencing an accident given that the customer is type B is 0.1. The problem asks you to calculate the probability that a new customer will experience an accident, but it doesn't tell you if the customer belongs to type A or type B. In other words, it asks you to calculate P of C, which is simply the probability of a customer experiencing an accident. We can also express P of C as P of C given S, and P of C given S is interpreted as the probability of C within the sample space of all customers containing both type A and type B. Since we know both the probabilities of C given A and C given B, we can calculate the probability of C. Now let's calculate the probability of C. P of C can be expressed as the probability of both C and A occurring simultaneously, plus the probability of both C and B occurring simultaneously. Let's discuss why. Event C represents an event of customers experiencing an accident, and it only has two possibilities. Either an accident experienced by a type A customer or an accident experienced by a type B customer. The probability of a customer experiencing an accident and belonging to type A can be expressed as the probability of the intersection of C and A. Conversely, the probability of a customer experiencing an accident and belonging to type B can be expressed as the probability of the intersection of C and B. Hence, P of C is equal to the sum of these two probabilities. Now, how do we calculate each probability? These two probabilities are not given in the problem, while P of C given A and P of C given B are given. Since we don't have enough space on the board, I'm not going to write the equation. But try to remember the equation for conditional probability. The probability of the intersection of C and A is equal to P of A times P of C given A. Similarly, the probability of the intersection of C and B is equal to P of B times P of C given B. Thus, the probability of C and A is 0.06 and the probability of C and B is 0.08. Therefore, P of C equals 0.14. This equation here is very important. Suppose we have an additional type D. Then the probability of C is equal to the sum of the probability of C and A plus the probability of C and B plus the probability of C and D. We can easily calculate the probability of C once we determine the probabilities of each intersection. Let's move on to the next problem. Given that a new customer had an accident, what is the probability that the customer is of type A? In this problem, the given condition is C, and the probability we are interested in is the probability of A. Thus, this problem asks you to calculate the conditional probability of A given C. Let's write down the equation for this conditional probability. P of A given C equals P of A and C divided by P of C. In the previous problem, we've already calculated P of C. We've also calculated the probability of the intersection of A and C as the product of P of A times the probability of C given A. You can calculate the probability of an intersection like this. Some people incorrectly calculate the probability of A and B as simply the product of the probability of A and the probability of B. Is the probability of an intersection really just the product of two individual probabilities? No. This is not true, so if you've been using this method, it's important to completely revise your understanding. The correct approach to calculate the probability of the intersection of A and B is to multiply the probability of A given B by the probability of B, or the probability of B given A by the probability of A. This is a more accurate method for calculating the probability of an intersection. The probability of A and B equals the probability of A times the probability of B only when a specific condition is met. Without this condition, the two are not equivalent. So if you have been calculating the probability of an intersection this way, please completely erase this misconception for now. In conditional probability, the probability of A intersection B serves as a numerator, and to find this, you multiply the conditional probability by the denominator, which is either P of B or P of A. Unless a problem specifically mentions about the relationship between the two events, P of A intersection B equals P of A times P of B given A. Earlier, I mentioned that the probability of the intersection of two events equals the product of the probabilities of each individual event only under a specific condition. The specific condition is the independence of the two sets. Events A and B are considered independent if the occurrence of one event does not affect the probability of the other events occurring. Here's an example of independent events. Imagine you're gambling and you've lost 5 games in a row. You might assume that the chance of winning the next game has increased due to the past losses. But in reality, it remains the same because each game is an independent event, unaffected by the outcomes of previous games. Similarly, the wins in prior games don't affect the likelihood of losing the next game. Again, each game is an independent event, and the outcome of the previous game has no effect on the outcome of the next game. Anyway, if events A and B are independent, the equation P of A intersection B equals P of A times P of B holds true. These principles are inherently intertwined. If the probability of A intersection B equals P of A times P of B, then A and B are independent. Conversely, if A and B are independent, the probability of A intersection B equals the probability of A times the probability of B. Additionally, if the two events are independent, the second equation also holds. The conditional probability of A given B can be expressed like this. And the probability of A intersection B equals the probability of A times the probability of B, and thus P of B cancels out. While we can understand why this equation holds true by deriving it from the first equation, there's a more intuitive way to grasp it. Consider B as a narrowed down sample space that satisfies a certain condition. Since A and B are independent, event B doesn't affect event A. So regardless of whether the sample space has been narrowed down to B or not, A remains unaffected by B. That's why the probability of A stays the same. Similarly, if A and B are independent, the third equation holds true as well. Regardless of whether the sample space has been narrowed down to A or not, the probability of B remains unaffected. When the two events are independent, the conditional probability B given A equals the probability of B. Now, let's explore the definition of dependence. Obviously, dependence has the complete opposite meaning of independence. Two events are dependent when the occurrence of one event affects the occurrence of the other, and vice versa. For example, many economic indicators such as the consumer price index and interest rates are dependent events, as changes in one indicator subsequently influence the other if we define the changes in the indicators as events. Let's consider two economic indicators, the consumer price index and the unemployment rate. If there's a rise in the consumer price index, it might lead to changes in consumer spending behavior, which could subsequently impact the job market and thus the unemployment rate. In this scenario, the two indicators would be considered dependent. When two events are dependent, the probability of A intersection B is calculated as we learned in the previous slide. Earlier, I mentioned that you should remember the second equation instead of the first equation, although the first equation holds true when A and B are independent. The reason why I emphasize the second equation is because assuming two events are independent is a very strong assumption, and in most real-world cases, it's nearly impossible. It's challenging to find two different events that are truly independent unless they exist in a strictly controlled environment. Therefore, in most situations in our life, we calculate the probability of an intersection using the equation below. Now, let's explore Bayes' theorem. The theorem is named after Thomas Bayes, a Presbyterian minister. He lived in the early 18th century and was also renowned as a mathematician and statistician. His contributions to probability were later recognized as foundational in the field of statistical inference. His work was so influential that it led to the emergence of a new branch of statistics called Bayesian statistics. Recently, Bayesian statistics has gained significant attention, similar to the rise of machine learning. This resurgence is largely due to the advancements in computing power and data storage, enabling more effective modeling and experimentation with Bayes' theorem. Indeed, understanding Bayes' theorem is crucial for anyone involved in data science. Bayes' theorem is a fundamental theorem in probability theory that describes how to update the probability of a hypothesis given new evidence. In other words, Bayes' theorem is a methodology of updating our initial guess based on new evidence. For example, when we encounter new data, it influences our initial hypothesis, leading to the formation of a revised hypothesis denoted as H1. Bayes' theorem precisely outlines this progression of updating an initial hypothesis when confronted with new evidence. Therefore, Bayes' theorem holds significant importance. In today's era of data-driven decision-making, it's commonplace for our perceptions or preconceptions to evolve with the introduction of new data. Bayes' theorem helps explain how our thoughts change when we get new information in terms of probability. Let me put it this way. Bayes' theorem describes whether the probability of my initial belief being true increases or decreases when we encounter new evidence. Hence, it's a crucial concept in statistics. Suppose we have events A1 to AN, and these events partition the sample space S. Each individual event has a probability greater than 0, meaning there are non-zero sets. When we talk about a partition, we are essentially describing the process of dividing a set into distinct, non-overlapping subsets. Partitioning a set involves dividing it into non-empty disjoint subsets in such a way that every element in the original set belongs to exactly one of these subsets. On the board, we have a quite complex-looking equation. However, we've already discussed each component. These two are probability, and this is a conditional probability. This equation is the mathematical definition of Bayes' theorem. Let's break it down even further. The left-hand side of the equation signifies the probability we aim to infer. We have a distinct term for this probability, known as the posterior probability of event A, given event B. The simple probability of A is referred to as the prior probability of event A. Lastly, the conditional probability of B given A represents the likelihood of event B occurring given event A. Now let's talk about the denominator term. The denominator on the right-hand side of the equation goes by various names, and I typically refer to it as the normalizing constant. Its role is crucial as it ensures that the result of the equation can be interpreted as a probability. In Bayes' theorem, the normalizing constant ensures that the posterior probability is properly scaled. This normalization process is fundamental for maintaining consistency and interpretability in Bayesian inference. Essentially, the normalizing constant transforms the numerator into a probability-like form. This implies that the numerator inherently encapsulates approximate information about the posterior probability of event A given B. Again, the purpose of the denominator is to scale the numerator, ensuring that the final result falls within the range of 0 to 1, which is essential for probabilities. Let's consider the scenario. There's a subscript k next to A. Suppose we have only two numbers for k, 0 and 1. For our illustration, let's associate 0 with a dog and 1 with a cat. Now imagine B as a specific model designed to detect either a cat or a dog from an image. This model, denoted as B, remains fixed throughout. P of A0 given B signifies the conditional probability that the model detects a dog, given that it's model B. Conversely, P of A1 given B represents the conditional probability that the model detects a cat, given that it's model B. Given that events A1 to AN partition the sample space S, it comprises only A0 and A1. In simpler terms, an image is either classified as a cat or a dog. Now let's revisit the normalizing constant. Within the normalizing constant, there is a summation operation where the subscript I iterates through every possible value for k. Imagine if we didn't include the normalizing constant in the equation of Bayes' theorem. The equation would return a value for each cat and dog. Remember, a dog corresponds to 0 and a cat corresponds to 1. For instance, let's say the equation returns 1.5 for a dog and 0.7 for a cat. Since the value for a dog is greater than for a cat, the image is more likely to be a dog. However, the value 1.5 exceeds 1. Furthermore, although A0 and A1 partition the sample space, the sum of these two values surpasses 1. By dividing the values by the normalizing constant, the sum of these two values equals 1, ensuring that our probabilities remain valid. Now let's consider a scenario where we have three values for k, 0 representing a cat, 1 representing a dog, and 2 representing a giraffe. Eventually, we'll obtain a value for each animal, indicating how likely they are to appear in an image. Without dividing each value by the normalizing constant, it's highly probable that the sum of these values won't equal 1. However, by dividing them by the normalizing constant, we normalize each value, ensuring they fit within the range of a probability which is 0 to 1. In summary, we can determine which animal is most likely to appear in an image even without the normalizing constant. However, the normalizing constant is crucial as it scales values to ensure they represent probabilities. Consequently, in practice, it's common not to compute the entire equation due to the complexity of calculating the normalizing constant. Instead, a simpler approach involves comparing the size of the numerator term for each value of k. Additionally, when events involve continuous variables, calculation of the normalizing constant involves integration rather than summation, further complicating the calculation process. Indeed, in practice, it's common to focus solely on calculating the numerator of the equation, even though the full equation includes the normalizing constant. Now let's explore the meaning of this equation. In the earlier example, B represented a specific model among many classification models. From the viewpoint of a decision-making model, B is a new evidence or data, while A represents an object of interest, such as the probability of a model classifying an image as a dog. To simplify, B signifies new evidence, while A represents a hypothesis. Thus, Bayes' theorem explains how our initial hypothesis evolves when presented with new evidence. Now I will explain why Bayes' theorem is powerful. Suppose we have 1,000 distinct classification models, and we've calculated a posterior probability for each model. Now, if 2 additional models are introduced, instead of recalculating posterior probabilities for all 1,002 models, we can simply update the existing posterior probabilities. This efficiency in updating probabilities rather than recomputing them for each piece of evidence illustrates the power of Bayes' theorem, particularly in machine learning and AI models. On the other hand, interpreting a prior probability is much simpler compared to a posterior probability. As we discussed earlier, a prior probability of events A represents the probability of the events occurring. Suppose we have 2 events A0 and A1, each representing a dog and a cat. If there are 10 dogs and 5 cats, then the probability for a dog is about 0.666 and the probability for a cat is about 0.333. In summary, a prior probability is calculated based on our own knowledge without any evidence or data provided. If we have sufficient data, a prior probability does not exert a significant influence on a posterior probability. However, as new data or evidence continues to be provided, probabilities will be updated accordingly. For example, if we receive additional cat data from an external source, the probability of a cat will increase, while the probability of a dog would increase with additional dog data. This concludes a brief explanation of Bayes' theorem. Up to now, we've been discussing probability. Now let's shift our focus and dive into random variables. This course leans more towards exploring the applications of random variables rather than just probability. Despite its name, it's important to note that a random variable behaves more like a function rather than a variable. Again, a random variable is a function rather than a variable. So what exactly is a function? Simply put, a function takes an input and gives you a corresponding output. Similarly, a random variable takes an input and gives back an output. Now, what do you mean by input and output in the context of a random variable? Well, the output of a random variable is essentially a real value, while the input represents an event. So, in other words, a random variable transforms an event into a real number. Remember our previous example? Events A consist of outcomes with exactly one head, right? Now, if a random variable were to take events A as its input, it might spit out a value like 0 or 2. Therefore, you can think of a random variable as a function that maps outcomes of a random experiment to real numbers. This idea helps us understand and predict uncertain events by turning them into numbers we can work with. A random variable assigns numerical values to events that occur with certain probabilities. Taking the example of flipping a coin twice, event A represents getting exactly one head. In this case, since there are 4 possible outcomes in the sample space and 2 of them belong to events A, the probability of events A is 0.5. This example illustrates how a random variable works. It assigns numerical values to events based on their probabilities. While the definition of a random variable may initially seem a bit complex, think of it this way. We start with an event, and a random variable simply assigns a real value to it. Finally, it's important to note that the possible values a random variable can take are determined probabilistically. Let's explore what it means for values to be determined probabilistically. Imagine a random variable that can take the values 0, 1, 2, and so on. These values are not assigned randomly. Instead, each value corresponds to a specific event. For example, let's say the events corresponding to 0 and 1 are A and B. Suppose the probability of event A is 30% and the probability of event B is 10%. Since the random variable assigns real values to events based on their occurrence, there must also be an event, say event C, mapped with the value 2. Let's assume the probability of event C occurring is 5%. In other words, the probabilities of the random variable returning values of 0, 1, and 2 are 30%, 10%, and 5% respectively. Theoretically, we could define a random variable as a function that returns symbols instead of real numbers. However, for practical applications such as creating formulas, functions, and graphs, using real numbers is essential. If a random variable were to return letters instead of numbers, it would complicate these applications. Therefore, random variables typically take an event as input and output a real number. Now let's consider the definition of a probability distribution. Earlier, I mentioned that a random variable might return values such as 0, 1, and 2. While these are integers, a random variable can indeed return any value within the real numbers. I also mentioned that each value returned has a corresponding probability. For instance, in the previous example, the probability associated with the value 0 was 30%. A probability distribution then maps the values of a random variable to their respective probabilities, and this mapping can be expressed through a table, graph, or mathematical function. Let's revisit the example of flipping a coin twice. We'll denote a random variable x as the number of times we get a head. Since x represents the count of heads, its possible values are 0 with no heads, 1 with only one head, and 2 with both flips resulting in heads. Each of these values corresponds to a specific event. Remember, an event is always defined as a set. For instance, the event associated with 0 heads is the set T and T, indicating both flips resulting in tails. Similarly, the event associated with 2 heads is the set H and H, and lastly, the event associated with 1 head comprises the outcomes HT and TH. Therefore, for every value returned by the random variable, there's a corresponding event. Moreover, for each associated event, there's an associated probability, denoted as f of x, implying that each value is associated with a probability. Given that the size of the sample space is 4, and there's only one outcome in the event associated with 0, the probability of this event is 0.25. Similarly, we can calculate the probabilities associated with other values as well. This table itself embodies the probability distribution. So if you're asked to determine the probability distribution of a random variable, creating a table like this is the way to go. While equations can also be used to represent the same information, both methods are equally effective in conveying the underlying probabilities. Let's dive a bit deeper into the concept of a random variable. Imagine we have a data set consisting of various heights. You could view this data set simply as a list of values stacked vertically, or you could conceptualize it as a random variable. How you approach the data set fundamentally changes depending on this perspective. Now let's say we choose to view height as a random variable. Just like with our previous example of coin flips, a random variable inherently comes with its own probability distribution. Once we've identified that our data set conforms to a particular probability distribution, we can proceed to align our data points with this distribution. This involves fitting our observed data to the expected probabilities outlined by the distribution. By doing so, we can effectively leverage the properties and patterns inherent in the probability distribution to conduct a more insightful analysis of the dataset. The characteristics of the distribution can encompass various factors such as the area under the curve, mean, or variance. When we analyze the original dataset, we can leverage these properties derived from the distribution. Moreover, although height data are typically collected by individuals, we can approach the dataset from a different perspective. Rather than merely viewing the data points as observations, we can conceptualize them as values generated from a random variable characterized by a specific distribution. This distribution has a peak at its center, indicating that values close to the center are more likely to be generated. Consequently, many values in the dataset are likely to cluster around the central point. Right? Conversely, if a value such as 2 meters appears in our dataset, it's likely to be located near the right end of the distribution. We can also quantify the likelihood of observing particular values within the dataset. Consider a scenario where we have a modest dataset consisting of only 50 data points. Attempting to determine the probability of encountering a value like 2 meters within such a small dataset might seem impractical. However, by treating height as a random variable and analyzing the dataset through the lens of the probability distribution that governs this random variable, we can do lots of new things. This approach enables us to conduct hypothesis tests, draw inferences, and perform various statistical analysis. Indeed, random variables play a significant role in statistics as they allow us to make meaningful assessments despite limited data. In statistical analysis, it's common practice to regard most data as random variables, forming a fundamental assumption in our analytical frameworks. The perspective that views data points as values generated from random variables is essential in statistical analysis. From now on, whenever we acquire data, we'll adopt the perspective of treating it as a random variable. For example, let's consider a data point such as 170 centimeters. If 170 centimeters is close to the average height, it's likely to be located near the peak of the distribution. Consequently, we expect numerous data points clustered around 170 centimeters within the dataset. This phenomenon illustrates a fundamental principle. The reason we observe more data points close to 170 centimeters compared to those near 2 meters is due to the underlying probability distribution associated with the random variable. This distribution assigns higher probabilities to values around 170 centimeters, thereby resulting in a greater concentration of data points in this area. Once again, please remember that the random variable is a crucial concept in statistics, and the probability distribution is a function that takes an event as input and returns a real value as output. Additionally, each event is associated with a certain probability. Do you remember the table we created earlier? In that table, each event was mapped to specific values like 0, 1, and 2. And the values were also linked with probabilities. Now let's explore different types of random variables. There are two main categories: discrete random variables and continuous random variables. If we can represent a probability distribution in table form, then the corresponding random variable is always discrete. In contrast, a continuous random variable can take infinitely many values, making a table unsuitable for its probability distribution. A discrete random variable has values defined within a discrete sample space. The value of a random variable is the output it assigns to an event. Please remember that a random variable is a function. It's also important to note that a discrete random variable is either finite or countably infinite. In the table we use for a probability distribution, the first row lists values corresponding to each event, and the second row lists probabilities corresponding to each value. We refer to the relationship between these values and probabilities as the probability mass function, or PMF. The PMF can be represented not only by the table itself, but also by an equation that describes this relationship. In other words, the PMF associates probabilities with each value of the discrete random variable. For example, if we have a random variable x and it can take values from x1 to xn, the PMF associates each value with its corresponding probability. The next category of random variables is the continuous random variable. A continuous random variable can take on values within a certain interval and has an infinite number of values. Additionally, we refer to the probability distribution of a continuous random variable as the probability density function, or PDF. It's important to note that the probability distribution of a continuous random variable is represented by the PDF, not the probability mass function, or PMF. So please don't confuse these terms. There's a reason why we use different terms for the probability distribution. When discussing discrete random variables, I mentioned that the PMF associates a probability of each value. However, with continuous random variables, the PDF doesn't directly associate probabilities. Instead, it associates something very similar to probability. Let f of x be the probability density function. This function is defined for a continuous random variable x. Additionally, f of x always has a value greater than or equal to 0, similar to the probability for a PMF. Let me add one more thing. If we integrate f of x over the entire interval, the result is 1. This is similar to the sum of probabilities being 1 in the case of the PMF for discrete random variables. Therefore, if you want to calculate the probability of a certain interval, say a to b, we take the integral of f of x over that interval. Let's see what it means. One of the most common probability distributions for continuous random variables is the normal distribution. You might think of the height or the y value as the probability associated with the x value. When we discussed the example of height, I also mentioned that height values around the center are more likely to be generated. Does this imply that the events near the center are more likely to occur compared to those farther away? Well, that's not entirely incorrect, but it doesn't mean that the probability of an event near the center is higher. Then what does the y value represent? The y value is not a probability, but instead, precisely speaking, it's the derivative of the cumulative distribution function. We're not going to discuss the cumulative distribution function in this course. You know what? Let's talk about the cumulative distribution function as well. The CDF represents the probability that the random variable x takes on a value less than or equal to x. The CDF looks like this. In the case of the cumulative distribution function, the y values represent probability. Let's denote the CDF as f. In mathematical terms, we can represent it as f of x equals y. Therefore, the CDF, or the function f, takes x values as input, and the output y represents the probability. Additionally, the precise definition of the probability y is the probability of values less than x. In other words, it's the accumulated probability of observing values less than x. Hence, the CDF provides a way to describe the probability distribution of a random variable by specifying the probability that the variable takes on a value less than or equal to a given point. Again, unlike the probability density function, the cumulative density function returns probabilities. Let's summarize. For a continuous random variable, the CDF returns probability while PDF does not. I will say it again since it's very important. The values returned by the cumulative distribution function are probabilities, whereas the values returned by the probability density function are not probabilities. Specifically, the PDF is derived from the CDF, and the value returned by the PDF is the derivative of the CDF. In other words, if you take the derivative of the CDF, you obtain the PDF. Thus, the y value of the PDF is not a probability. Despite not being probabilities, we often use the PDF more than the CDF because it's easier to identify characteristics of the distribution with the PDF. If you examine the graph of the CDF, you'll notice that the y values are always larger for the x values on the right side. Although the x values clustered at the center are most likely to be generated, it's hard to tell from the graph. Therefore, we calculate the derivative of the CDF and plot the PDF, which shows a peak at the center. Now with this graph, it's much easier to identify the values that are most likely to appear. Thus, graphically, the PDF represents the distribution's shape and characteristics more directly, making it easier to identify features such as peaks, skewness, and tails. Now, you might be wondering, can we just associate each value with a probability like the PMF? Unfortunately, it's impossible. Suppose we have a value 0 for a random variable x. Let 0.01 be a probability associated with 0. Then, we need to associate probabilities for 0.001, 0.0001, and so on. There are infinitely many options x can take, and if you associate a probability for the infinitely many values, the sum of the probabilities will exceed 1. No matter how small a probability we associate with values, the sum of the probabilities will equivalent to infinity since there are infinitely many values. Thus, in the case of a continuous random variable, the probability of a specific value is always equal to 0. Once a probability associated with a specific value exceeds 0, the total probability becomes infinity, which violates the axiomatic definition of probability. So how do we calculate the probability for the PDF? In this case, we calculate the probability of an interval instead of a specific value. For example, the probability of a height being exactly 170 centimeters equals 0. If we say that the probability of a height being 170 centimeters is, let's say, 1%, the total probability becomes infinity. Thus, to maintain consistency with the axiomatic definition of probability, we calculate the probability for an interval. To calculate the probability for an interval, we determine the area within that interval. This area represents the probability for the interval. As mentioned earlier, the PDF is derived from the CDF by differentiating the function. Unlike the PDF, the CDF returns probabilities, and the derivative of the CDF is the PDF. In other words, if we integrate the PDF, we can obtain a probability. When applied to functions, integration calculates the area under the curve of the function over a given interval. right? Again, integration calculates the area under the curve, and the probability density function represents the derivative of the cumulative distribution function, which yields probabilities. By reversing the differentiation, we can obtain a probability, as integration undoes differentiation. This is why we calculate the area within a given interval. To summarize, there are two reasons why we need to calculate the area. First, we cannot measure the probability of a specific value for a continuous random variable. Second, since the PDF is the derivative of the CDF, integration is necessary to obtain a probability. Let's recap for the last time to ensure clarity. For a continuous random variable, we have two functions, the CDF and the PDF. The CDF provides probabilities directly, while the PDF yields the derivative of these probabilities. In other words, the y value we derive from the PDF represents the derivative of probabilities. So, to obtain probabilities, we integrate the function. Right? Additionally, through integration, we assess the area under the curve of the function across the specified interval. This clarifies why measuring the area is essential for probability calculation. Did you get it? The PDF is derived from the CDF by differentiation. To revert to the original state, the PDF needs to be integrated. Integration involves measuring area, making it essential for continuous random variables when calculating probability. I repeated the same explanation over and over again because it's a very important concept. I hope you now understand why integration is necessary for probability calculations. Also, remember why we cannot calculate the probability for a specific value of a continuous random variable. Assigning probabilities to specific values violates the axiomatic definition of probability, which states that the total sum of probabilities must equal 1.